हेलो स्टूडेंट्स, हाउ आर यू? कैसी तैयारी चल रही है? वेलकम टू माय चैनल. If you have not subscribed my channel yet, please subscribe it. Today I shall discuss one important topic in inorganic chemistry, which is periodic variations of atomic and ionic radii. If you are preparing for 12th board exam or IIT or NEET exam, then there are at least 4 to 5 questions from this section. So this section is important for competitive examination point of view, also in the point of view of your board examinations. The periodic variations of atomic and ionic radii. First, I shall consider the in a period. What is the variation of atomic or ionic radii in a period? With the change of atomic number in periodic table, the atomic and ionic radii changes. Let us consider in the case of a period. We see that in a period with increase of atomic number, the atomic or ionic radii decreases. Let us consider the elements of second period. In the second period, the elements are lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. And the atomic number increases. Lithium has atomic number 3, beryllium is 4, boron 5, carbon is 6, nitrogen 7, oxygen 8, fluorine is 9. But if we see the covalent radii in angstrom, then it is decreasing. 1.23, 0.90, 0.82, 0.77 and fluorine has 0.72. Thus we see that in case of second period elements or in periodic table, the alkali metals, the first group is alkali metals. Alkali metals have largest covalent radii, while if we consider in the same period, if we consider the halogens or inert gas elements, then they have the smallest size. Therefore, we can say that in a periodic table, in a period, the size decreases from alkali elements to halogens. Now, how can we explain this variation? Explanation, how can we give the explanation of variation of these covalent radii? We see that when we move left to right in a periodic table, the atomic number, that is nuclear charge, increases. The number of electrons also increases, but electrons are being added to the same main energy level. Electrons are added to the same main energy level. No extra new energy level is formed. Therefore, the distance between the nucleus and outermost shell of electrons remains almost the same. But with the increase of atomic number, the nuclear charge also increases. Here there are 3 protons, 4 protons, 5 protons. Therefore, nuclear charge increases. Therefore, the electrostatic attraction between the nucleus and valency shell electrons increases. Therefore, the size of atoms or atomic radii or covalent radii decreases. Thus, we can explain when we move in a period from left to right, the size of atoms decreases with the increase of nuclear charge. Since the electrons are added to the same energy level, no extra or new energy level is formed. Similarly, if we see the variation of atomic or ionic radii in a group, we see that in a group, when we move in a group downwards from top to bottom in a group, with the increase of atomic number, the size of atoms increases. Let us consider the second A group elements. Let us take the elements of second A group. These elements contains alkaline earth metals, beryllium, magnesium, calcium, strontium and barium. Here we can see that covalent radii gets on increasing 0.90 angstrom, 1.36, and barium has 1.98 angstrom. Similarly, ionic radii of divalent cations also goes on increasing from beryllium to barium. Thus, we see that when we move from top to bottom in a group in periodic table, the size of atoms or ions increases. Now, how can we explain these variations? This can be explained on the basis of two forces. When we move downwards in a group from beryllium to magnesium, the number of electrons increases, therefore the mean energy level also increases. Energy cells are successively added in the atom. Therefore, the distance between the nucleus and valency cell electrons increases. Therefore, the electrostatic force of attraction goes on decreasing. The electrostatic force of attraction goes on decreasing. Since the distance between the nucleus and outermost cell of electrons are increasing, because new main energy levels are being added in moving from beryllium to barium. For example, if we consider beryllium, it has atomic number 4, its configuration is 1s2, 2s2. In case of magnesium has atomic number 12 and its configuration is 1s2, 2s2, 2p6, 3s2. Thus we see that in case of magnesium, electrons are present in second energy level, but in case of magnesium, electrons are also present in third energy level. Therefore, the distance between the nucleus and outermost cell of electrons increases, thus the electrostatic force of attraction decreases. Now, when we move from beryllium to barium, it has atomic number 4, 12, calcium 20. Thus, the nuclear charge also increases, number of protons also increases. Therefore, the electrostatic force applied on valency cell of electrons increases. The net effect of these two opposite forces is that the electrostatic force of attraction between the nucleus and valency cell electron goes on decreasing as we move downwards in a group. So the size increases when we move from beryllium to barium. Thus we see that in a group the covalent radii or ionic radii goes on decreasing downwards. Next, I shall consider the size of isoelectronic spaces. This is the size of isoelectronic spaces. Isoelectronic spaces can be defined as the atoms or ions having the same number of electrons. The number of electrons is same. For example, if we take nitride ion, its atomic number is 7 and number of electrons is 10. But again, in case of oxide ion, it has atomic number 8 but number of electrons are 10. Similarly, in fluoride ion, atomic number is 9 but number of electrons are 10. Thus, these are the isoelectronic spaces, since the number of electrons are same but the atomic number are different. If we take the ionic radii of these isoelectronic spaces, we see that the ionic radii goes on decreasing with increase of atomic number. 7, 8, 9, 10, in case of neon it is 10. Thus we see that when we increase atomic number of isoelectronic species, the ionic radii goes on decreasing, the size decreases. This can be explained on the fact that in each case the number of electrons are same, but the nuclear charges are different. in case of nitride ion, there are 7 protons. Therefore, the attractive force between the nucleus and valency shell electrons also goes on increasing with the increase of nuclear charge. Therefore, the size goes on decreasing. The size decreases with the increase of atomic number. Since the electrons are being added to the same energy level, no extra or new energy level is formed. In case of nitrogen, oxygen, fluorine, electrons are being added to the same energy level. Next is the size of cations, size of same cations having different oxidation state. For example, if we take iron 2 plus, iron is present in plus 2 oxidation state, also in plus 3 oxidation state. This is known as ferrous ion and it is called ferric ion. It is called ferric ion, it is known as ferrous ion. Thus we see that the size of ferrous ion is larger than the ferric ion. This thing can be explained on the basis of Z upon E concept. Z upon E concept. Z is nuclear charge, E is number of electrons. In case of ferrous ion, Z upon E ratio is 26 upon 24, but in case of ferric ion, Z upon E ratio is 26 upon 23. Thus, Z upon E ratio in case of ferric ion is more as compared to ferrous ion. Therefore, the electrostatic force of attraction is more effective in case of ferric ion, thus its size decreases. Similarly, we can explain the size of atom and its cation and anion. We can compare the size of an atom and its cation and anion. If we take, for example, if we take fluorine, in case of fluorine, its size is 0.72 angstrom, but when we form fluoride ion, its size increases. It is 1.36 angstrom. This thing can be explained on the basis of Z upon E ratio. In case of fluorine, the Z upon E ratio is fluorine has atomic number 9 and 9 upon 9, but in case of fluoride ion, the Z upon E ratio is 9 upon 10. Since one more electron is being added in fluoride ion, therefore the Z upon E ratio is 9 upon 10. Thus, Z upon E ratio is more in case of fluoride ion, more in case of fluorine as compared to fluoride ion. Therefore, the size of fluorine is smaller than the fluoride ion. Similarly, here we can see that the size of sodium atom is larger than sodium ion. Sodium atom has size 1.90 angstrom, but the sodium ion has size 0.95 angstrom. This thing can also be explained on the basis of Z upon E concept. In case of sodium atom, atomic number is 11 and number of electrons is also 11. But in case of sodium ion, atomic number is 11, but the number of electrons is 10. Sodium ion is formed by the removal of one electron from its outermost shell. Therefore, in case of sodium ion, Z upon E ratio is larger than sodium atom. Therefore, the size of sodium ion is much smaller than the size of sodium atom. Thus, today I have discussed the variations of atomic and ionic radii in periodic table. We have seen that in a period, the atomic or ionic radii decreases when we move from left to right. For example, in second period, when we move from lithium to fluorine, the covalent radii goes on decreasing. This is due to fact that the number of cells remains the same, but the nuclear charge goes on increasing, therefore electrostatic force of attraction increases, therefore size decreases. But in a group, for example in second A group, when we move downwards, the size goes on increasing. This is due to the decrease in electrostatic force of attraction due to increase of distance between the nucleus and outermost shell of electrons. Similarly, we have discussed the size of isoelectronic species having same number of electrons. With the increase of, here we have seen that in the increase of atomic number, the size of isoelectronic species goes on decreasing. Size goes on decreasing. This is due to the increase in nuclear charge. Number of electrons are same, nuclear charge are increasing, therefore the electrostatic force of attraction increases, therefore size decreases. In case of ions, same ion having different oxidation state, the size of ion having lower oxidation state is more than the in higher oxidation state. This thing can be explained on the basis of Z upon E ratio. In case of ferric ion, Z upon E ratio is larger than in case of ferrous ion. Similarly, the size of a parent atom can be compared with its cation and anion. The size of fluorine atom is much smaller than the size of fluoride ion. And in case of sodium atom, the size of sodium atom is much larger than the size of sodium ion. This thing can also be explained on the basis of Z upon E ratio. Thank you for watching my lecture. Your comments are welcome. This topic, periodic properties, atomic and ionic radii variation, is important from the point of view of board examinations and also from the point of view of NEET and IIT-JEE examination. At least 3 to 4 questions are asked from these topics. If you study carefully, then you can easily attempt the questions. Thank you for watching my channel. If you have not subscribed my channel yet, please subscribe it. Thank you once again.